We're going to continue discussing Newton's laws of motion by going over his second law. Obviously, you know to hold an object, you have to exert an upward force to oppose the gravity of that object, especially heavy sorts of things. You know that they're going to fall to the earth if you don't provide some type of force or some type of effort to keep them from doing so. So if you release this object, it's going to accelerate downward due to Earth's gravity. So as we can see, unbalanced forces are going to cause accelerations. Consider this spring scale. Notice that when there's no mass hanging on it, the force red is obviously 0. Once we place a force on it, we have this force we're going to label force 1, F1. When we hang two masses of the same size, we see what happens, that the spring scale reads double the force of 1, which we're going to call F2. So let's say we take that F1, that force, and we move to an air track, and we pull a car along with that same force. We're going to observe an acceleration we're going to call A1 when that force 1 is applied. Now below, we put twice the force on the object, and what happens? We get twice the acceleration. For this reason, acceleration is directly proportional to the force placed on an object. That object's acceleration, I should say, is proportional to the force. Now, on the other hand, mass tends to resist change in motion. So the more mass I have, if I'm using that force F1 to pull at a constant force, I'm going to get an acceleration A1 on that mass. However, if I put double the mass attached, as you see in the bottom picture, if I put double the mass on with that force F1, I'm only going to get half the acceleration. As I up the mass, I get less acceleration. If I were to decrease the mass, I would get more acceleration. So as you can see, acceleration is inversely proportional to mass. As mass goes up, acceleration goes down. You can obviously see that in this picture here. The little tugboat's going to have an awfully hard time pulling that large cruise ship, whereas the hockey player on the right is going to have less of a hard time stopping that hockey player that's falling, because obviously the hockey player has a lot less mass than the ship. Changing something's motion depends a lot on its mass. So because we know those relationships, we can put it in this equation form for Newton's second law. The acceleration is equal to the force divided by the mass. Notice as the force goes up, the acceleration goes up. As the mass goes up, the acceleration would go down, since it's on the denominator. You might have heard that written F equals ma, a good summary of Newton's second law. Now, of course, this only deals with one application force, but there might be several forces acting on an object. We're going to label that sum of the force vectors. We can either call it F sub net, the net force, or we can call it this sigma notation F. Sigma F means the sum of all the forces combined. So that's all that sigma means, is total or sum of all the forces. So we're going to write this equation as the sum of all forces equals the mass times the acceleration. So an object of mass m has an acceleration vector a equal to the net force vector F divided by the mass m. Notice the acceleration and force are vectors, so if a net force is applied on something, that object is going to move in the same, it's going to accelerate, in the same direction as the net force is provided. It won't necessarily be moving in the same direction. If you consider throwing an object up, the gravity force pulls down, and the acceleration of the object is down, even though the object might be moving upward. So the direction of an object's acceleration is the same as the direction of the net force acting on it. This also applies in every direction of your coordinate system. So in the x direction, the net force is going to equal m times the acceleration in the x direction. And in the y direction, the net force will equal mass times the acceleration in the y direction. It's important to break your vectors up into their components to fully understand that object's motion. Finally, z direction, which is pointing in and out of the screen, obviously your net force there is also going to equal the mass times acceleration in that direction. So if an object has no net force acting on it, in other words, the sum of the force or the net force is equal to 0, we can then conclude that its acceleration must be 0. So if its acceleration is 0, its velocity must be constant. We measure force in a unit called the Newton. And a Newton is defined as the force required to give 1 kilogram of mass an acceleration of a meter per second squared. If you take a look at the math here, 1 Newton, if a force, is equal to 1 kilogram mass times 1 meters per second squared acceleration. So 1 Newton can be defined as a kilogram times a meter per second squared. So 1 kilogram meter per second squared is how we define a Newton. Just to give you an idea, a quarter pound is about how much a Newton weighs. So let's take a look at this example here. The net force acting on a car has a magnitude of 540 newtons. If the car's acceleration is 0.39 meters per second squared, what is its mass? So we're saying the net force equals 540 newtons. We're saying the car's acceleration is 0.39 meters per second squared. We want to try to find the mass. So in this case, we're just going to apply Newton's second law. We know that the net force equals m times a. So therefore, if we solve for m, we know that the mass is equal to the net force divided by the acceleration. In this case, 540 newtons divided by 0.39 meters per second squared, and that's going to give us a result of 1384. With sig figs, it'll be 1400 kilograms. Well, notice newtons divided by meters per second squared will give us kilograms, given the definition of a newton being kilogram meters per second squared, because these meters per second squareds cancel out and we're left with the unit for mass. So it's often helpful when we're dealing with Newton's laws to draw free body diagrams labeling all the forces on those free body diagrams. And in the next video, we're going to go ahead and take a look at how we draw a free body diagram, treating an object basically as a point particle, meaning all its mass is concentrated in a single point. So we're going to take a look at how we sketch those and also how we can apply those to problem solvings in Newton's second law.